Alright, geometry, lesson 20, applications of congruence in terms of rigid motion. Okay, lots of reading again for this lesson, and then we'll do a few examples. Actually, there's 3 examples, which shouldn't take us more than 10 minutes, but let's get through the reading part. Hold on, have to move that. Can't really see it. There we go. Every congruence gives rise to a correspondence. Okay, when two things are congruent, it makes pieces and parts corresponding to each other. Under our definition of congruence, when we say that one figure is congruent to another, we mean that there is rigid motion that maps the first onto the second. That rigid motion is called congruence. If we say that, under our definition, we say that one figure is congruent to another. If there's rigid motions, maybe it's just a translation. That means that one figure is mapped on to another. The rigid motion is called congruence. So we would say triangle ABC is congruent to triangle A prime, B prime, C prime. Okay, the whole 7th grade reference isn't really relevant to you guys since you didn't use this textbook in 7th grade, but correspondence between two triangles is a pairing of each vertex of one triangle with one and only one vertex of another triangle. When reasoning about figures, it is useful to be able to refer to corresponding parts. Corresponding parts is what I've always talked about with when things are congruent or similar in geometry. We'll get to similar another day. But it's useful to be able to refer to corresponding parts, which are sides and angles of the two figures. A correspondence between two triangles is a pairing of each vertex of one triangle with one and only one vertex of another triangle. We look at one part of the first figure and compare it to the corresponding part of another. Okay, these are all things that I'd probably be highlighting if I were on paper. We look at one part of the first figure and compare it to the corresponding part of the other. Where does a correspondence come from? We might be told by someone how to make the vertices correspond. Conversely, we might make our own correspondence by matching the parts of one triangle with the parts of another triangle based on appearance. Finally, if we have a congruence between two figures, the congruence gives rise to a correspondence. Alright, a rigid motion F always produces a one-to-one correspondence between the points in a figure, the pre-image, and points in its image. When they refer to this, it's like we're talking function notation. Oops. So I'm going to repeat that. A rigid motion F always produces a one-to-one correspondence between the points in a figure, the pre-image, and points in its image. Okay, if P is a point in the figure, then the corresponding point in the image is F of P. A rigid motion also maps each part of the figure to a corresponding part of the image. As a result, corresponding parts of congruent figures are congruent. This is actually a theorem that I would use all the time. Corresponding parts of congruent figures are congruent. When we use it in proofs, we would say corresponding parts of congruent figures are congruent. CPCFC. So as a result, corresponding parts of congruent figures are congruent since the very same rigid motion that makes the congruence between the figures also makes the congruence between each part of the figure and the corresponding part of the image. In proofs, we frequently refer to the fact that corresponding angles, sides, or parts of congruent triangles are congruent. This is simply a repetition of the definition of congruence. If triangle ABC is congruent to triangle DEF because there is rigid motion F such that f of A equals D, f of B equals E, and f of C equals G. Pause. Not literally pause, but let's just draw that. That was awful. We said A, B, C. Say there's some rigid motion. We're just going to say a translation because it's easiest to describe. If we do f of A equals D, that means I'm going to write a D over here. F of B equals E, and f of C equals G. So the function at A translates to D, B translates to E, and C translates to G. Excuse me. That does mean that segment AB is congruent to segment DE, which is right here. Then triangle ABC is congruent to triangle DEG, and so forth, because the rigid motion F takes segment AB to DE and angle BAC to EDF. BAC to EDF. Okay, we're saying that because triangle ABC is congruent to triangle DEG, then all of the segments are congruent to their corresponding segment, segment congruent to corresponding segment, segment congruent to corresponding segment, etc. Also, the angles are congruent to the angles, etc. Okay, that's that CPCFC. Corresponding figures are congruent. There are correspondences that do not come from congruences. The sides and angles of two figures might be compared even when the figures are not congruent. For example, a carpenter might want to know if two windows in an old house are the same, so the screen for one could be interchanged with the screen for the other. He might list the parts of the first window and the analogous parts of the second, thus making a correspondence between the parts of the two windows. Checking part by part, he might find that the angles in the frame of one window are slightly different from the angles in the frame of the other, possibly because the house has tilted slightly as it aged. He has used a correspondence to help describe the differences between the two windows, not to describe a congruence. Okay, it's a great description. He's comparing two things, so he's using a correspondence. He's comparing them to describe the differences, not to describe how they're equal. In general, given any two triangles, one could make a table with 2 columns and 3 rows, and then list the vertices of the first triangle in the first column and the vertices of the second triangle in the second column in a random way. This would create a correspondence between the triangles, though generally not a very useful one. No one would expect a random correspondence to be very useful, but it is a correspondence nonetheless. I think I would look at this word as comparing. Okay, you're not comparing things that are congruent. I think there's an I there, I hope. Okay, later when we study similarity, similarity is not congruence. We find that it is very useful to be able to set up correspondences between triangles, despite the fact that the triangles are not congruent. Correspondences help us to keep track of which part of one figure we are comparing to that of another. It makes the rules for associating part to part explicit and systematic so the other people can plainly see what parts go together. When we do similarities, we'll compare triangles, but they won't be equal. That's an awesome line right there. So we're going to compare part to part, but they're not going to be equal parts. They're not going to be congruent. Okay, discussion. Let's review function notation for rigid motions. A, to name a translation, we use the symbol T with AB array. We use the letter T to signify we are referring to a translation, and the letters AB to indicate the translation that moves each point in the direction from A to B along a parallel line AB by distance AB. Now I was just looking at the test we're going to have very, very soon, and it's really important that we understand these 3 steps. So that's your little hint right there. Let's see. To name a reflection, we use the symbol R and then a little L, where L is the line of reflection. The image of point P is denoted reflection over line P. In particular, if A is the point on L, the reflection on L of A equals A. That means this is L, and that is A. So the reflection of point A over line L is point A because it's on the line. For any point P, the line L is perpendicular bisector. I made that a little too long, so we'll just go here. For any point P, line L is the perpendicular bisector of segment P over reflection of line L to P. Okay, so this line right here is perpendicularly bisected. This segment is equal to this segment. To name a rotation, we use the symbol R small c x degrees. This to remind us of the word rotation. C is the center point of the rotation, and X represents the degree of the rotation counterclockwise around the center point. Note that a positive degree measure refers to a counterclockwise rotation, while a negative degree measure refers to a clockwise rotation, or we would just write the word or the letter CW after it. Okay, in each figure below, the triangle on the left has been mapped to the one on the right by a 240-degree rotation about P. Identify all 6 pairs of corresponding parts, vertices and sides. So I'm just going to label A, B, C, and what do they map onto? So if we look, A maps onto X. No. That is wrong. I said X. I circled Y. There we go. A goes to X, B goes to Y, C goes to Z, which means AB goes to XY, BC goes to YZ, and CA or AC goes to ZX. I just paused it because there's a mistake there and I was trying to figure it out, and now I can't. Okay, CA goes to XZ, which is what I wrote the first time. Goodness, it was right. Sorry. One of the little, if you need a trick, once we get our angles down, it's really easy to get our sides. Notice I just went for the pre-image AB, BC, AC, or CA. AB, BC, AC, which gives us XY, YZ, and XZ. Cool. What rigid motion mapped triangle ABC onto triangle XYZ. This would have helped us too, right? Write the transformation as function notation. So we did a rotation about P, 240 degrees, triangle ABC to triangle XYZ. Given triangle with vertices ABC, list all possible correspondences of the triangle itself. Okay, we're doing just correspondences now. If you remember, for a triangle, I have 3 vertices and 3 vertices each triangle. So I'm actually going to have 6 correspondences. Let's see. We're going to go A to A, B to B, and C to C. Then we'll go A to A, B to C, and C to B, A to A one more time. Nope. Sorry. A to B. Pretty simple. A to B again. Oops. Let's do that first column so I don't forget anything. And then A to C. Cool. I just didn't want to forget them in the right order. Alright, we're on number 4. So we just did A to B. Let's do B to C and C to A. And then A to C, we can do B to A and then C to B. And then we'll do A to C, B to C, and C to A. If you notice, all 6 of them, I've got my first columns, and then I just change up the second ones to give you a pattern to hopefully follow. Alright, 9. Give an example of 2 quadrilaterals and a correspondence between their vertices such that A, corresponding sides are congruent, but B, corresponding angles are not congruent. 2 quadrilaterals, okay? Oh, geez. That means 4 sides. Goodness, let's see. I could do a trapezoid and a rectangle, but this side doesn't match that side, so that doesn't work. Ooh. Parallelogram. That's terrible looking. Let's see if I can make that a little bit better. Parallelogram. And a rectangle. So we're going to make these congruent, those congruent, but none of those angles are congruent. So A, B, C, D, E, F, G, H. Now it says correspondence between their vertices. So A to E, B to F, G to C, and H to D. A, B, C, D. Yeah, cool. One thing I want to point out, it's very common to start and to go into in a circle to name things. Okay, and unfortunately it's very common to go clockwise, even though all the rotations we've been doing have been counterclockwise. Exit ticket. I included the exit ticket to just give us something else to talk about for the lesson, because I thought the lesson was pretty short. What is a correspondence? And why does a correspondence what is a correspondence and why does a congruence naturally yield a correspondence? I'm going to try something. Okay. We'll see how this works. So, a correspondence, that's really big type, between two triangles is a pairing of each vertex of one triangle with one and only one vertex of the other triangle. I love spell check. The pairing can be expanded to figures other than triangles. What else? Looking through the notes. Congruence naturally yields a correspondence since a rigid motion maps each part of a figure to what we call a corresponding part of the image. Cool. Last question. Each side of triangle XYZ is twice the length of each side of ABC. Fill in the blanks below so each relationship between lengths and sides is true. So this is actually, a little pre-lesson on similarity. Okay, we're increasing by a factor of 2, okay, which you see right here. So in essence, AB times 2 is XY, and BC times 2 is YZ. And then finally, CA times 2 is ZX. And that's all for today.